Hello, hello everyone. Welcome to a new virtual tour of the European Southern Observatory, or simply ESO. It's acronym. My name is Farid Char, and with the producer Hector Salas, we are going to be your guides during this trip to the ESO Paranal Observatory. Just a little bit about me. I have more than 15 years of experience in astronomy outreach and education. I am one of the guides of the observatory since 2010, and so I have been working in astronomy outreach for a long time, um, and working, of course, in this important observatory, the most advanced observatory on Earth. Okay, and as I told you, I am not alone. I am with producer Hector Salas. So, how are you, Hector?
Hi Farid, I'm happy to be here once again. So I'll introduce myself. My name is Hector Salas. I'm a PhD student at the Leibniz Institute for Astrophysics in Germany. I work mostly with topics related to the circumgalactic medium, that is the environment that surrounds galaxies. And I have been a member of the team of guides for Paranal Observatory since 2019. I started while I was doing my master's degree in the University of Antofagasta. And today I will be the producer, and that means that I will be switching the pictures, the videos, but I will also be reading all your comments and questions. And during the tour, Farid will give a couple of moments to answer any doubt you might have. So please send all your comments and questions to us.
Thank you very much, Hector. So, yeah, ESO wants to be with you during these virtual visits and bring astronomy directly to your home or wherever you are. So please remember, you can send your questions and comments during all this streaming. So I can imagine you already have some questions. So we are going to answer some questions later in some portions of this virtual experience. Okay. Okay. So we are going to start immediately, and we are going to help you to understand the place of our visit. So we will begin with some information about the European Southern Observatory, or ESO. So ESO is composed of 16 member states. Okay. In a few moments, we will see this screen right now. So we can see the ESO member states. The headquarters of ESO are located in Germany, and also Australia has joined ESO as a strategic partner. In this case, Chile is the host state and the home of all ESO observatories. So from the 1960s, and with those objectives in mind, ESO has chosen one of the best places on the planet for astronomical observations, the Atacama Desert in Chile. So during this period, Chile started several site explorations in order to attract international observatories, such as ESO, to our country. As a result, Chile offered its territory, and ESO did choose the more suitable areas. So the mission of ESO is to design, build, and operate astronomical observatories. And what for? To enable important scientific discoveries and incentivize the promotion and cooperation in the astronomy field. So right now you will see a picture with the three observation sites of ESO in Chile. So here is the Chacnator Plateau, the site of the ALMA and APEX radio telescopes. ESO is part of these places for radio astronomy alongside other international partners. In addition, south of the Atacama Desert at 2,400 meters, we have La Silla Observatory in the Coquimbo region in Chile. So this ESO observatory is the home of several telescopes, such as the NTT, or the 3.6 meter ESO telescope. And this one is using the HARPS instrument. And this one is an exoplanet hunter. And finally, we have the place of our visit, the Paranal Observatory. This ESO observatory is the home of the Very Large Telescope, or VLT, the most advanced visible light telescope on Earth. In the next few years, we will also have the Extremely Large Telescope, or ELT, and this will be the biggest visible light telescope. So, and something else, near Paranal, we will have another facility. It's called the CTA South, and this will be an array of different telescopes focused on capturing gamma rays. Okay, so now we have a better picture. So let's travel to the Paranal Observatory. So virtually, right now, you are flying over the Atacama Desert in the north of Chile, about 1,600 kilometers north of the capital Santiago, specifically about 130 kilometers south of Antofagasta, the regional capital, and about 90 kilometers north of Taltal, the closest city. So now we are going toward the mountain top of Cerro Paranal, located at 2,600 meters above sea level. This mountain belongs to the coastal range, and despite its altitude, it is located at just 12 kilometers from the coast. And where's the ocean? Well, the Pacific Ocean is located below of the cloud cover. And why those clouds, if right here the sky is so clear, dry, and lonely? Well, this is because of the influence of the Humboldt Stream. This is a cold stream near the coast of Chile and Peru, cooling the atmosphere and causing a phenomenon called thermal inversion at about 1,000 meters above sea level, keeping below the cold, humid, and basically bad air for astronomy. Above the layer, instead, we have the hot, dry, and less dense air. So this is something like the good air for astronomy. The clouds are blocked by the coastal range, and near Paranal, the mountains are high enough, surpassing 2,000 meters above sea level. Now, we have more natural barriers around this area. For example, about 200 kilometers to the east, we have the Andes Mountains, with very high mountains, more than 6,000 meters above sea level. So this is another natural barrier blocking the clouds from Argentina and Bolivia. So the main result is this landscape, a place with an average of more than 300 clear nights per year, with a very clear and transparent atmosphere, making it ideal for observing the night sky. Also, we are far away from artificial light sources because of human activity. I mean, light pollution. So, this is one of the best places on Earth for astronomical observations. Okay, so right now we will change the view to make to have a closer look, an even closer look to Paranal. So as you can see here, this is not an ordinary mountain. And now we can see the different telescopes and structures in the mountain. We are at the summit of Cerro Paranal. Do you know what Paranal means? Well, in the Quechua language, Paranal means whirlwind, possibly because of some whirlwinds forming in the desert. However, as I told you already, the atmosphere here is extremely quiet. So this observatory is a true oasis. You will see how in one of the driest deserts we have a lot of life and of course a lot of science. Okay, so right now we will visit the summit of Paranal. Okay, so right now in front we have the very large telescope or the VLT, its acronym. Okay, so if you see the amount of buildings, I mean four giant domes and other four small and rounded ones, I mean these ones, it's clear that the very large telescope, in fact, is not only one, but a very special array of telescopes. So all this facility is the most advanced optical observatory on Earth. So let's take a closer look. Here you can find the four unit telescopes, or UTs, each one with a primary mirror of 8.2 meters of diameter. So the giant ones in your screens. And the other small ones are the auxiliary telescopes, or ATs, each one with a primary mirror of 1.8 meters of diameter. So here we have one, here's the second, there's another one there, and this is the last one. Now, coming back to the big telescopes, each UT has a name in Mapudungun language. This is the language of the Mapuche culture, natives from central and south of Chile. So here we have Antu, which means sun. This one is Cuyen, which means moon. Right here we have Melipal, which means 4 stars, but this word is related to the Southern Cross constellation. And here we have Jepun, so this word is a reference to the planet Venus. And as I told you before, the other telescopes here are the auxiliary telescopes. Now, the small ones are very special because they are mobile and they can be moved using a rail system, this rail system. So you can see we have some stations there, right? So we can move the small ones up to 30 different positions on this platform. So we have more um, rails and stations over there. So they were specifically designed to work all together as a single big telescope with a variable diameter. So it's basically this system is basically able to reach up to 200 meters, as you will see in a few moments in a short video. Okay, so the technique to combine the light from several telescopes is called interferometry. So with this technique, we are able to observe much more specific details if you compare this with the individual telescopes. Now, thanks to interferometry, we can simulate a giant mirror to distinguish details up to 16 times fainter than a single telescope. So why don't we make small telescopes and combine them to create a huge telescope? Well, interferometry also has limits, and some information is lost during its travel. However, it is still an excellent solution to observe objects too difficult to observe with our current technology. Okay, so right now we will come back to the tour screen. So now we will have the opportunity to visit one of the telescopes. We are going to visit the UT3 Melipal, this one. We can't enter all the telescopes, but don't worry about that because the 4 ones are identical in size and shape. So the only difference are the instruments inside. Of course, you can learn more about the instruments on the ESO website. Okay? Okay, so now we are going to enter this telescope. We are going to visit the UT3. And here we are. So this is the Melipal telescope. So what can you see? This is a giant telescope, right? So at this moment, we are on the last floor of this telescope at the same height of the main mirror in front of us. So the mirror there, and I will show you, I will do a close-up. This mirror has 22 tons with 8.2 meters of diameter and only 17 centimeters thick. It was created from a ceramic and flexible material. This material is called a cerodur. And the surface is a very thin layer of aluminium. So this is the reflective material there. Now, of course, we are talking about a big and heavy telescope, okay? So anytime when we move this telescope to different positions in the sky, um, this mirror is curved, okay? It's like a spoon. This mirror, because it's too heavy, can suffer some distortions or deformations. But of course, we don't want to break this mirror. So how can we point this telescope to the sky without breaking it? Well, we have to explain something about a mirror and a very specific technology applied on the mirror, but I need to explain this from this level. Okay, this is like the ground level. So right now, as you can see, we are in a different floor of the telescope structure, and we can take a look at the mirror from this position. So, so basically the mirror, as you can see, is mounted over this white structure. Okay, this structure is like a cell supporting all systems assisting the mirror, including something called active optics. And here you can see some gray boxes. I will show you. I will do another close-up. Here we have some gray boxes. You see? So they are called actuators. So they are a kind of piston, and we have 150 in total. And all those actuators are controlled by computers. So they are acting on the mirror during the observations in order to keep the optimal shape of this concave mirror. Okay, so please remember the mirror is concave, it's like a spoon. So otherwise it could suffer deformations just because of gravity or physics. Okay, so those deformations, even imperceptible in a first view, could be critical in the result of the observations. So that's why we need the active optics here. Okay, so um, now we need to explain a little bit how this telescope is observing at night, how this telescope is working in combination with the instruments. Okay, so for example, you can see this is one of the instruments. Okay, the other instruments are in the opposite side there and in the bottom there. And here you can see some engineers working on the instruments and the telescopes during the day. But now we have to explain a little bit how this telescope is observing at night. So now we are going to watch a short animation, and I am going to explain how this telescope is working. So the first step, of course, is to open the dome. Of course, this is exaggerated. So the first thing that will happen is that the light is going to impact the primary mirror. The light will be concentrated, it will be reflected to the secondary mirror in the top, and it will be reflected again to a tertiary mirror. So the light will be eventually received by the instruments. The instruments are those red, blue, and green boxes there. So essentially we can take advantage of three different instruments, okay? One instrument at each time. So um, eventually the instruments will convert the physical light into a digital signal, okay? And this digital signal will be transferred by fiber optics to the control room. So there is another location, another facility with all the astronomers and the scientists working at night, and this is the control room. So we are going to visit the control room in a few moments during this virtual experience. But this is the important process here, okay? So just to summarize, this is the primary mirror, concave, okay, 8.2 meters. In the animation, we saw the secondary mirror. The secondary mirror is this one. This mirror is convex. And there is another mirror, it's a tertiary mirror, but it's not visible here because we have this structure blocking the view. But the tertiary mirror is basically in the middle. Okay, so in the middle, this mirror, there is a hole in the middle. Okay, so we have a tertiary mirror there, and this mirror will reflect this light to this instrument, to the other instrument in the other side, or this tertiary mirror can be lifted. So we can expose the hole in the middle so the light can go directly to the instrument in the bottom, okay, this one. So this is what happens during the night. Okay. Um, and as I told you already, we have engineers working during the day. So basically, in Paranal and any modern observatory, uh, the work during the day is for engineers, and the work during the night is for astronomers. So they are basically doing calibrations, they are doing maintenance, they are fixing problems, this kind of stuff. And during the night, we are observing with the telescopes. Okay, so this is basically what happens in Paranal. Okay, so this was the explanation about this telescope. So now we are going outside, and as I told you already, the next stop will be here. This place is the control building. In this place, we have the astronomers working at night. This is the opposite view. So you can see that it's a big facility. And this will be our next stop. But before going there, I don't know, Hector, if we have some questions so far.
Uh, we have some greetings. We have George who says hi from Mexico. We have Sway Graven, a regular viewers. We have Kim saying hi, and George has a question. What is the longest observation that the BLT has made? And do the astronomers in the BLTs use the UTC time for their observations?
Well, if the question is talking about like the longest project, maybe maybe we can talk about this observation of the black hole for several years, right? I don't know if this is the exact question here,
That's a good.
or if it's talking about exposure time.
Yeah, no. If we're talking about exposure time, the data that well, he just said yes. So about exposure time, the data that I'm currently using for my PhD thesis was taken with the UT4 with the instrument Muse, and is 150 hours of exposure time,
Oh,
which is
well,
a lot.
yeah, sure.
I'm not sure if there are longer projects, but I was surprised when they told me that this area of the sky, that is the same as the Hubble Deep Field, was being observed for 150 hours of time.
Thank you,
Mhm.
Hector. Oh, well, and regarding the other question, well, the UTC is this is about the universal time basically, and the answer is yes. It's actually any astronomical facility, any astronomical record is recorded in universal time because, well, you can, well, the most obvious reason is because you can avoid any ambiguity when you are, sharing this observation with any other observatory. So for example, the universal time is the same in Chile, in USA, in Australia, in Japan, in any country. So uh, anytime you need to report an observation for any reason, any astronomer will know the exact time of the observation. So you are not committing mistakes about local time, daylight saving time, or all of this. It's a general rule in astronomy.
Okay, and I don't see any more questions, so let me ask you one of the usual questions people make in Paranal. What kind of maintenance is necessary for the telescopes?
Well, sure. We can come back to the telescope to explain a little bit about that. Of course, the mirrors are the most delicate part of this telescope. So, so the first kind of maintenance, or the easy maintenance on the mirrors, is something that you do with a specific element, with the carbon dioxide snow. This is something like a foam. So you need to apply this foam into the mirror. So you need to rotate the mirror a little bit, and a couple of engineers They are going to spread this carbon dioxide snow, and this is in order to remove dust because we are in the desert. So we have a lot of dust in the environment, and we need to remove dust, and this is like the easy way to do it. Okay, so you need to do that about once a month, and that's enough to keep the mirror clean in general terms. But you need to do an additional maintenance, and this is more complex. You need to do something every 2 years. You need to remove all this mirror from the telescope. And in order to do that, you need to extract the mirror. Okay, we need to use a special door to remove the mirror. So let me go outside because I can show you quickly. Um, for example, just next to Jepun, if we do a close up, you can see a yellow structure there. Okay, so basically, when we remove the mirror will be placed here, and we need to um, drop the mirror very gently, of course, and and the mirror will be received by a special vehicle. So this vehicle will transfer the mirror down to the base camp, and we need to move the mirror to another facility. We need to move the mirror to the mirror maintenance building, and in that place, we need to do a recoating. Okay, so the recoating is basically to remove the aluminum layer and put a new one. So at the end of this process, that it takes about 3 or 4 days. At the end of this process, we can bring the mirror again to the platform. We can lift the mirror using this this structure, and we can reinstall the mirror in the telescope. And basically, the mirror will look like a new mirror because you are essentially changing the surface. So the aluminum surface will look like new, and it's like you have a new mirror. But in fact, all the mirrors in all the four telescopes are the same original mirrors from more than 20 years, but they look the same because the recoating has been done several times.
Okay, thank you. I think we can continue for the tour, but I remind our viewers that they can send us any doubts, comments, and questions that they have, and we have a second chance during the tour to answer anything that you might want to address.
Okay, thank you, Hector. So yeah, we are going to move to the next stop. We are going to the control building. As I told you before, we had the scientists working here. So we are going to access the control room, and here we are. So if you look carefully, this place is essentially an office space. So we have several separated workstations. Okay, so we have workstations for each telescope. So in this case, this workstation right here is for one specific telescope, Melipal. You see, if you see, we have the Melipal telescope plaque here. So we have several computers for different purposes, and we have a few people working here at night, but working specifically on the UT3. Now, if we move to the opposite workstation, we have um, Jepun, right? So this is the workstation for Jepun only. So we have again some computers, some monitors for different purposes, and we have some scientists working here. Okay, um, we are going to keep working using this virtual corridor to show you the last workstations. And here we have the workstation for AN2, UT1, you see. Again, different computers. And in the opposite place, we have the last workstation for Guyana. Okay, so essentially, all the systems, telescopes, and everything I was explaining before is controlled from here. Okay, during the day, the engineers, technicians, and scientists are working to prepare the telescopes for the next observation night. So each night we have a telescope operator and an astronomer per telescope. So in order to explain that, I am going to, let's say, access to this workstation. So for example, in this workstation, we can see, again, some computers. This person is a telescope operator, okay? So this person is in charge of the technical details and the movement of the telescope. So this person is like the pilot of the machine. Now, the ESO astronomer is in charge to direct the scientific observations, and this person will decide the next steps. So the astronomer is like the co-pilot. Okay, so let's suppose this person is the astronomer. Now, of course, the observations are performed by experts from ESO for scientists from all the world. Okay, so this is basically what happens here. And this place is again is like an office space. The people working here will remain all night, and we don't need a lot of people. We need maybe 2 or 3 people per workstation. Okay, so they are basically supervising the observations from this comfortable space, and they need to stay here until till the next sunrise. Okay, so that's it. This is what happens here at night. So now I am going to come back, because now we have something very interesting to show you. Because now you have a lot more information about the observatory and the people working here. But now I want to invite you to know more about the main scientific milestones made from all ESO observatories. I mean La Silla, Paranal, and Chajnantor. So the scientific staff from different countries are using the ESO telescopes to study objects near to our home, the solar system, but also others located in the more distant places in our universe. So now we are going to explore a list of the top 10 discoveries from ESO sites so far.
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang Theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam, or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Okay, so this was the top 10. But we have just one more thing. We have something like a bonus track. So let's take a look at this right now. This is a little bit older news, but of course it's very, very important. A team of astronomers were able to capture the first picture of a black hole. So the Event Horizon Telescope, or EHT, its acronym, an array of 8 ground-based telescopes distributed on the planet, working as an international collaboration, was able to achieve the first direct evidence of a supermassive black hole. So the picture will reveal the black hole in the center of Messier 87, a massive galaxy in the close galaxy cluster in the Virgo constellation. So this object is located 55 million light years from Earth, and its mass is about 6,500 million times the mass of our Sun. Okay, so we hope you liked the top 10. This was only a fraction of the discoveries thanks to the ESO telescopes and the scientific stuff behind them. So now we can continue And from the platform again, we are going to do a very special activity thanks to this virtual tour. We are going to observe the night sky from Paranal. So as you can see, the sky is almost completely dark, with the last traces of light from the twilight. And the moon is below the horizon, and the sky, of course, is full of stars. So we are going to navigate for some very popular objects here. So first, if we look just above the ANTU telescope, we are going to focus on this very popular constellation. This is Orion. So we are going to do a close-up, and I will show you this constellation. In the mythology, it represents a hunter. Now, you can recognize it with those three stars, somewhat aligned, representing Orion's belt. And inside of Orion, we can see another interesting object. We have the Great Orion's Nebula here. So we are doing another close-up, and you can see it. Now, this object is very, very bright. So you can see the Orion's Nebula even with your naked eye. And of course, if you try to observe this with binoculars or and even small telescopes, it looks very, very bright. Of course, if you try to observe this with a professional telescope, you have a lot of details. So the Orion's Nebula is basically star-forming region, and is a very popular object for observers from the north and south hemispheres, because this constellation can be observed from both hemispheres. Okay. Now if we move a little bit from Orion, we will look at this very bright star. So this bright star here, its name is Sirius. This star belongs to the Canis Major constellation, and it represents Orion's hunting dog. Now, the importance of this star is that this is the brightest star of the night sky. So Sirius, in this case, is another object that is visible from observers from the north and the south. And the constellation of Sirius, Canis Major, is basically connected in the mythology to Orion. Now, a little bit down, if we come back to ANTU, we can see that just next to ANTU here, we have something else. We have this. This is the Pleiades. This is an open star cluster, and this is located in the Taurus constellation. Okay, so this is again a very popular object for north and south hemispheres, because you can see this from both areas. And in this case, is visible next to this telescope. Okay. Now, the majority of those objects are visually close to a very specific area, very populated with a lot of stars. I mean, if you look at this area, you can see that we have more concentration of stars, right? If we compare with this area or this area. Okay. So actually, here you are looking at one of the Milky Way arms, and this is our galaxy. Okay, so and our sun is only one among hundreds of millions of stars. So during the winter in the southern hemisphere, we can see the center of the Milky Way, and this is another full area, another area full of stars between Scorpius and Sagittarius constellations. Okay, and you can see all this area from this hemisphere, from the southern hemisphere. Okay, now we are going to change the view. We are going to rotate a little bit because I want to show you these two spots in the sky. So now we have this spot here and this one right here, and it's very interesting because they look like clouds, and the name of those objects are actually the Magellanic Clouds. Up there, we have the large Magellanic Cloud, and down here, we have the small Magellanic Cloud. But they are not clouds, actually. They are galaxies with an irregular shape, and both of them are visible to the naked eye in a clear night like this one. But in this case, you can observe those galaxies only from the southern hemisphere. Okay, so the name, the Magellanic Clouds, refers to the records from Ferdinand Magellan during its circumnavigation of the planet in the 16th century. So during this time, the people were unaware about what a galaxy is. Okay, so that's why at that time the people was looking at this and they thought that these were clouds. Okay. So another interesting area next to the Magellanic Clouds is located right here. This is the smallest constellation in the sky. This is the Southern Cross. Okay, in this case, it's a little bit tilted. This constellation is, well, again, only visible from the southern hemisphere, and in this case, it's a very good guide to find the South Celestial Pole. This is basically a projection of the Earth's South Pole. So during the night, the stars appear to revolve around this point. So because in the southern hemisphere, we don't have any bright star next or near the South Celestial Pole, I mean, in the northern hemisphere, the northern observers, they have Polaris. But in the south, we don't have any bright star. So the only way to do it and to find this area is to have some assistance from the Southern Cross, because you can project the longer stick here 4.5 times. So if you project this like 1, 2, 3, 4.5, more or less like here, you have the South Celestial Pole. So during the night, the stars appear to revolve around this point. Okay, and if you look to the horizon, I mean, if you outline a straight line to the horizon from here, basically you are looking at the south cardinal point. Okay, so this is something like a good technique to find the cardinal points in case you are lost in the desert. Well, so this is basically the conclusion of this quick navigation in the night sky. So now I am going to come back to the telescopes, and I am going to change the view to show you daytime again. Because now we are going to start to close this virtual experience with a quick visit to another interesting area. This is the residence of Paranal. So in order to visit the residence, we have to go down to 2,400 meters, I mean, to the base of the mountain. So basically, we have to visit the base camp of Paranal. So as you can see, in this area, we have the base camp. We are going to visit this place because, well, the base camp is basically all those facilities there with some rooms for contractors. We have the mirror maintenance building. We have other facilities to fix or to do maintenance on some pieces and materials. We have more offices there. So basically, this is like a mini city in Paranal. But here I want to show you specifically the residence. The residence is this area here with this sort of dome, because in this place the ESO staff can stay and rest. Okay, so the residence is the home of the ESO staff when they are working in the desert. As you can see, we have to access using this ramp. And this place looks like underground, but it's actually taking advantage of the shape of the land. Okay, so we are going to access the residence here, and you can see that this place is very interesting. It's beautiful, of course. We have um, we have a swimming pool, we have vegetation. So the first important thing is that we have a more humid air. We have green areas, and we have a much more comfortable space if we compare with the desert in the outside. Now, in this place, we have 108 rooms. So this is something like a hotel, but it's not for tourists. It's for the staff only. Uh, Over there, we have the restaurant. So anyone working in Paranal can go there to eat. Here we have the lobby, we have the reception. So it's similar to a regular hotel, but it's only for the staff. Most of the rooms are basically crossing this corridor there. So as I told you already, we have 108 rooms, and but it's only for the people working for the observatory or also visitor astronomers coming from other countries. Okay, so at this point, I think we have some time to answer the last questions, Hector.
Sure, we have some more greetings. We have Mara from Pordenone in Italy. We have also from Helios from Porto Alegre in Brazil. And George has another question. Is it true that pulsar's fast rotation moment can be used for precise timekeeping? And the answer is more or less yes, that pulsars have a very precise rotation. I was trying to look if there is actually a clock using this or some type of time measurement, and apparently there is a clock that uses pulsar time that exists in Brussels. And what I do know also is that um, the moment of pulsars is so precise that if for some reason it's disturbed, you can try to do some calculations using Newtonian physics and estimate if there is a planet there. And actually, one of the very few, very early exoplanets discovered was discovered by this technique that they call pulsar time. So, yes. I don't see any more questions, so I'm going to ask one. Is it possible for our viewers to go in person to the observatory?
Yeah, that's right. Visitors can go to Paranal every Saturday. We have visits at two times, 10 a.m. and 2 p.m. The visit takes about 2 hours and a half. Usually, the visitors are coming from Antofagasta, so the driving time is about 1 hour and a half. But of course, I recommend to start your trip at least 2 hours in advance. Um, so you need to do an online booking. For that, you need to access the ESO website, and you need to find the public visits section, and you can find all the necessary information to do an online booking. And again, I recommend to do that with some time in advance, maybe 2 weeks in advance, because we have limited spots. So we are doing the tour in Spanish and English. So we welcome Chileans and international visitors every Saturday.
Okay, thank you, Fred. And with that, I think we are on time to end today's tour. For my part, I say goodbye and thank you for viewing us today. Please remember that we are having these spiritual tours every Saturday. We're alternating between English and Spanish, between Paranal Observatory and La Silla Observatory. So keep an eye out for when the next tour is going to be and what it's going to be about.
Yeah, sure. So, well, from my side, I just want to remind you that all these visits, information, and pictures are available on the ESO website. And I hope you like this virtual experience. So please stay alert to the next um, uh, ESO virtual tour. So, well, see you again in our next time. Thank you very much, and see you.